Welcome back to Dave Does Math from Home. We're doing part 3 of our video series on section 17.1, which is about vector fields. We are learning how to graph vector fields and what vector fields look like, and we are thinking about the flow or the force that these vector fields represent. If there's some sort of water current or air current or electrical current or magnetic field or force field. These vector fields exist because they're a great way for us to model things pushing on other things. So it's important to think about, if this is a magnetic field, what happens if you drop an iron marble into it? If this is a water current, what happens if you drop a little paper boat onto that surface of water? Or if it's a water current, what happens if you drop a little motorboat onto that surface, and then you want the motorboat to travel in a certain path? Like, how much resistance is it going to get from the water? How much help is it going to get from the water? That sort of thing. That's all going to be very, very important for various aspects of electrical engineering that I personally do not understand. Please ask an electrical engineering professor about those. But we've done that. We've graphed our vector fields. We know what that looks like. This video is going to be about determining when curves are tangent to vector fields and when curves are perpendicular to vector fields. So I want to start with my not my favorite vector field. I think a good vector field. F of x, y equals negative x, negative y. This is a variation of what I described in the last video as the explosion vector field. The explosion vector field was everything goes straight out, directly away from the origin. This is that, but negative. So in this one, everything is going straight in towards the origin. This is the implosion vector field. So if something is really, really far away from the origin, it gets a big vector that goes straight to the origin. If something is really, really close to the origin, it gets a small vector that points straight to the origin. So this is the black hole, if you will. But again, I guess a black hole would have stronger pull the closer you are, weaker pull if you're far away. So anyway, I want to know where this thing is either tangent or perpendicular to the curve C is x squared plus y squared equals 9. So this is my curve C. It's a circle, radius 3. This is the implosion vector field, everything's coming in. We can probably, based on what this looks like and based on what this looks like, we can probably already start making some educated guesses about where it's tangent and where it's perpendicular. But I'm not going to make educated guesses because I want to use this as an example to show you how to do all of the work for this in cases when we don't have educated guesses to make. So we're going to do this one the hard way. If we're interested in finding vectors that are normal to this curve, we already have tools available to us that can tell us about vectors normal to a curve. And that's the gradient. Hopefully we remember from when we talked about gradients that gradients are always perpendicular to level curves. So if you have some surface, the gradient points in the direction of steepest ascent on that surface, and the level curve is a path of no ascent or descent. So the gradient points steepest, level curve is no change. The negative gradient would point in the steepest descent, and all those things are perpendicular to each other. So the gradient with its steepest ascent has to be perpendicular to the level curve with its zero ascent. So this, some circle, we're going to pretend that this circle, x squared plus y squared, is 9 in particular. We're going to pretend that this is actually just the level curve of some potential surface, phi. Don't ask me why they chose to use phi for this, right after we used phi for an angle in spherical coordinates. I don't have the answer to that question. Some old dead mathematician one day decided that we were going to use phi for potential functions, and now we do, and I guess we just deal with it. So we're going to say that there's some potential function phi, which is this function x squared plus y squared, and that this particular curve is just one level curve of it. This is the phi equals 9 level curve of this larger potential function. Now that we have a larger potential function, we can find the gradient of phi, and that should be 2x plus 2y as a vector. No, sorry, 2x comma 2y. I apologize. 2x comma 2y as a vector. This is the derivative with respect to x, I, the derivative with respect to y, j. This is our gradient function of the gradient of the potential function that has this level curve. And this gradient we know is perpendicular to the level curve all the time. So this vector field is always perpendicular to this thing. And we can use that. To find points of tangency. So if it's tangent, the vector field, here's my circle. This is the curve C. Perpendicular to the curve C is our del phi. This is the gradient of the level curve, or gradient of the potential function, perpendicular to the level curve. And we have this function doing things here. If we want points where the function is tangent to the level curve means perpendicular to the gradient of the potential function. So tangency means perpendicular to gradient of the potential function. And we can see whether this function is perpendicular with this function by taking the dot product. F dot del phi is going to be negative 2x squared minus 2y squared. If we want these things to be perpendicular, we have to set that equal to 0. There's two ways we can proceed from here. One is we can sort of look at this function and we can say, all right, the only way negative 2x squared plus y squared equals 0, the only way this equals 0 is when x squared plus y squared equals 0. And the only way that happens is at the point 0, 0. 0, 0 is not on this curve. So we can say that doesn't happen. The other way to look at this is if we're on this curve, x squared plus y squared equals 9, so we can say that this is negative 2 times 9 equals 0, and we can tell that that's not true, which also tells us that there's no points of tangency. So this is how we find points of tangency. Assume that the curve is the level curve of a potential function. Take the gradient of the potential function. Find the dot product between that and your vector field and try to set it equal to 0. That'll tell you where it's tangent. Because we know this is always perpendicular to the curve. So if something is perpendicular to the thing that's this is perpendicular to the curve and it's also perpendicular to this, that means that this is tangent to the curve. Perpendicular to the perpendicular, in this case, means tangent. But there are none of those. We found no points of tangency. This vector field is never tangent. Which sort of makes sense because we know that this vector field is like doing implosion looking things. So it's kind of coming inward. It's never going across. It's always going in. So the next question then becomes, how can we find points of perpendicularity? We know that this vector field is never tangent to this curve, because there's no points of tangency, but we want to find points where this vector field is maybe perpendicular to the curve. And to do that, we need to add another layer of perpendicularity here. We determine tangency by looking at things that are perpendicular to the perpendicular. We determine perpendicular by trying to find things that are perpendicular to the perpendicular to the perpendicular, which sounds really, really terribly confusing, and it is pretty confusing, but if you work through all of those layers of perpendicularity, I think you will find that it is in fact still perpendicular. So let's see what that looks like. I'm going to have to erase this tangency stuff. We still have phi as our potential function, that this could conceivably be a level curve of. We still have this as a gradient. Now we need to create n. N is going to be a new vector field that is always perpendicular to this. I don't care what other characteristics it has, I just need it to be always perpendicular to this. And the easy way to create something that's always perpendicular like that is flip the order of them and make one thing negative. Doesn't matter which one. If you flip the order and make something negative, then you'll always be in a situation where if you try to take a dot product of these two things, you'll get 4xy negative 4xy. The things will always cancel if they're flipped and one's negative. So this is how I've created my new normal vector n. So this n is always perpendicular to this, which is always perpendicular to this. So this is two layers of perpendicularity. I'm going to test to see if n is perpendicular to f. And that's my third layer of perpendicularity that will actually test for perpendicularity. To test for perpendicular, see where f is perp to n, which is perp with del phi, which is perpendicular with c. So once again, we have C is a curve, delta phi, or del phi, I keep on calling that a delta. That's not a delta. Delta, the triangle on a delta points upwards. Del points downwards, and means gradient. So we have our curve C. Del phi is always perpendicular to that. N is always perpendicular to the gradient, and we are testing now to see if f is perpendicular to n. If f is perpendicular to n, that means that it's perpendicular to c. That's sort of the goal here. Perpendicular to the perpendicular to the perpendicular. It's a lot of perpendiculars, but it's the easiest way to do this, trust me. So, if we want to test where f is perpendicular with n, we need f dot n, which will give us negative 2xy. plus 2xy, which is 0. So if this is 0 always, all the time, doesn't even matter what x and y are, then the field F is always perpendicular to C, which is hopefully what you were sort of expecting when I said that we can probably puzzle this out based on what things look like. C goes around, F always points straight inwards. So hopefully we were already thinking that F is perpendicular to C everywhere. The implosion vector field always perpendicular to a circle around the origin. But now we've proven it mathematically, and it has given us the tools to be able to do this on other problems. So I do want to do one more example of stuff that looks like this. I don't think I'm going to finish that in the next 3.5 minutes, so I'm going to start a part 4. Won't be long. Stay tuned.